So, hello everyone. Welcome to the fourth talk in our series What Is. Uh, Today's speaker is Trishan Mondal from Remath third year. He'll be talking on what is cohomology. His interests are primarily in algebraic topology. Over to you, Trishan.
Groups are basically a module over Z, and basically here we can take the coefficient over any arbitrary ring. Let me move forward. So, and here delta I, this is the map. Uh, this is basically restriction of the map sigma I have defined there to the opposite vertex of ith vertex. So basically, if everybody can see this board here. So here, if I label like 0, 1, 2 to this triangle, so the sigma 2 will basically be the sigma and its restriction to this 0, 1 only. So this is what I mean by the restriction. So now from the above thing, I will define a differential delta q that is a map from this delta qx to delta q minus x. This is defined by this. So whenever we have a continuous map sigma, we will uh, delta q will take this to the summation up to some sign to this sigma I, and here it can be verified that delta this composition of delta q and delta q plus 1 is 0. And so we have this sequence where composition of two consecutive differential is 0. In general, we call them chain complex, and for this case, for this setup, we will call them a singular chain complex. So once we have so yeah, for the case of cohomology, we just need a cochain complex. It doesn't matter from where it comes. So basically, when we have a chain complex, we can just apply the Hom functor to it to get a corresponding cochain complex. And in this case also that this delta, their composition will also be 0. I mean, the consecutive composition of two delta will also be 0. So such those things we call as a cochain complex. And once we have cochain complex, we can define cohomology like this. And in this setup, we will call this a singular cohomology. And basically, this cohomology measures how far this sequence is from being exact at the point Q. Okay, so now I will define something called relative cohomology. So for that, we need a subspace of X. So for this case is also again, we can define cochain complex that is the set of all homeomorphism from this delta q to I mean this quotient to z basically, and it can be again shown that this forms a cochain complex, and the corresponding cohomology we call a cohomology of pairs or relative cohomology. And okay, so with this, I will define some properties that can be checked, not very easily, but that can be checked that these properties holds. So the first property is this HQ x comma a, that is relative cohomology, that is a covariant functor from this pair of topological space. So basically, here if I write HQ of this is a functor from top square to abelian group in this setup. So it doesn't matter. And now this is the condition that if I have a given a point for that the 0th cohomology would be z, and it will be trivial for higher dimension. This is called dimension axiom. Okay, and it can be seen later like these are all this property if we have a set of covariant functors which satisfy all these conditions, that will give us a corresponding cohomology. Okay, so now I will define this exactness. So whenever we are given a pair of a pair x comma a, there will be a long exact sequence like this. And yeah, and now I will define the excision property. This is very interesting property for the case of ordinary homology theory, that whenever we have a closed subset U, this closed subset U of A inside X, and this U has to be closed inside A. Okay, then this natural inclusion will induce isomorphism in the cohomology. And again, there is this property, this additive axiom or additive property, that whenever we have disjoint, uh, um, yes, disjoint pairs, then their union will be the, I mean, the cohomology of their union will just be the product of the cohomology. And okay, I just want to mention, if you have seen, for the case of homology, is will be just the direction. So yeah, and this is the homotopy axiom. So if f from x to y is a homotopy equivalence, then it will induce isomorphism in cohomology groups. Okay, so yeah, this is what I was talking about. This set of axioms, we call it Eilenberg-steenrod axiom. If any set of contravariant functor satisfy this from the homotopy category, homotopy category of topological space to the pair of modules, then it will give us this will give us a cohomology theory basically. And yeah, I just want to mention something like this. In this axioms, if I remove this dimension axiom, then we will call that cohomology theory as extraordinary cohomology theory. I think in Somo's talk you will see like generalized cohomology, or kind of, yeah, you will might see the generalized cohomology theory. They are not a ordinary cohomology theory. Okay, so now I just want to move. Oh, and also one important remark, that any ordinary cohomology theories are equivalent. And by equivalent, I mean at each dimension, they will give kind of isomorphism. So if we fix the base ring to be the same, and yeah, and here, so this is one of the important features of cohomology, that it gives us a graded ring structure very naturally. Like, so here this delta is just a diagonal map from x to x times x, and so, and the map is also very natural. Basically, every point x goes to x comma x. So since we know that this cochain complex is kind of a contravariant functor, so it will give us a map that is delta star from ck of x times x to ck of x. And there is some theorem by Punet that I will use here. That, okay, let me write it here properly. Sorry for this. Okay, sorry for this. So this is the Punet theorem. So in general, if we have two topological space x times y, this will be isomorphic to this direct sum. Okay. So here is this k denotes the Punet isomorphism. And sorry for that. This I mean, you should not confuse this k with this k. This k is just into some isomorphism, and this k is some index. Okay. So from here, I can define a product structure very naturally. So yeah, this is the product structure. So here A and B, their product is defined to be this. So basically, you take one element A from this pth cochain complex, and one element B from this qh cochain complex, and call them like they have degree P and Q, then their product. So basically, you are looking their image under this composition, that will maps to that will maps to the case thing, which is basically P plus Q. So basically, if you have a element A which has degree P and a element B which has degree Q, then their product will go to somewhere that has degree P plus Q. Okay, so this gives us a very graded ring structure for this cochain complex, and it can be shown that this differential, I mean, if I apply the differential to the product, it will split like this. So basically, this is what we call Leibniz formula or something like that. And yeah, so from here we can see that it respects both the boundary and co-boundary. So basically, we can define this product in the cohomology groups. And yeah, So this is the and the direct sum corresponding in the cohomology group, we call it cohomology ring, and this product will again give a graded ring structure here. Okay. So now I want to give some examples of cohomology ring just by so one will be some computation and one will be very abstract kind of thing. So here is the first example, that is for torus. So here this torus is basically if you guys have I mean if you guys are familiar with the identification spaces, then you know that torus is basically nothing when we have a square and their sides are identified like that. And now we will take a simplicial decomposition of this torus like this. So basically, this triangle and this triangle are the two simplices for this torus. And since all the vertices are identified, there is only one, I mean, zero-dimensional simplex. And these sides A and B will give us corresponding one-dimensional simplexes. So for this, if you apply the definition of cohomology that I have defined previously, you will see that the cohomology group of the torus is this. So for 0 and 2, this is Z, and for otherwise, this is the direct sum of two copies of Z. And so, yeah. So now we will define, I mean, we will try to see what is the cup product structure here. And suppose alpha and beta are the generators of this first cohomology group of the torus. So basically, in this case, we have, so if everybody can see this board or this board. So basically, we have yeah. So we have only two sides. I mean, only two one-dimensional simplices. So here this alpha. So remember, what is what is the quotient complex in this case? That is delta q. This is basically a form of delta q to z. So basically, this alpha and beta, they I mean, they denote some kind of morphism. So basically, alpha is the morphism that take a to 1 and b to 0, and beta is similar thing for B. So this is what I mean by that alpha and beta are generators. So now what we want to see their cup product structure, that alpha. So here I want to mention one more thing. So when we have alpha, this belongs to call delta, yeah, call it delta P of X. And if we have beta, that belong to delta Q of X, then alpha, beta, as we have seen from the graded structure, it will be just this. And when it applies to a simplex, call it that have p plus q vertices, so call it, so this is the representation of the p plus q dimensional simplices, then this will give us just these things: alpha on the first p things and beta on the next p things, q things, sorry. So this is what I mean by this uh, cup product structure for the case of singular or simplicial complexes. So yeah, so here you can just compute it like for all this. So here we have seen that we have only two sets. So for those, if we compute all the cup products, so this will be like this, except for this 0, 1, 2. Other for other things, everything will be 0. So basically, what can we say? We can say that this alpha union beta generates not union alpha cup beta generates the cohomology, two-dimensional cohomology, and this has this relation that yeah. So this has this relation that alpha square and beta squares are 0, and alpha beta is equal to minus beta alpha. So this is so any Z module which look like this is known as exterior algebra. So it can be proved in general also that for if we have the product, so we know that torus is a product of I mean product of two S1. So in general, if I have a space that is product of circles, so for that case also this will be, I mean its cohomology ring will be exterior algebra, which is basically a Z module generated by xi's, and xi xj is equal to minus xj xj if I not equal to j, and 0 if I equal to 0. So basically I have generalized this idea, and the proof will be kind of same. So also, I forgot to mention some properties. Like if I have yeah. So if I have two spaces, then the cohomology ring, call it x. So if I have two spaces X and Y, for that this cohomology ring will just be their tensor product. So basically, this thing follows from this way. Okay. Now I will do one more computation that will be useful when I will define top invariant or H spaces. So yeah. So for this case, we need Poincare duality. I think most of you might have familiar with. Yeah, so you have to fix a base field, sorry, base ring that I have said. Then all of these are will be a module over that ring, right? So for that case, it will be a tensor. So if the base ring is up, so there will be a. Uh, so yeah, so now I will define. I mean, I will present a form of Poincare duality. This is not the exactly Poincare duality that you have seen. So yeah, so this is the Poincare duality. So basically, what it says is, so if M is a n-dimensional, uh, if M is a n-dimensional closed orientable manifold with a fundamental class M. Okay, just for this moment, fundamental class is a generator of Hn of, this is homology Hn of M. So it can be shown for a case of closed manifold. This is basically, if I fix a ring R, then this is basically isomorphic to R. It can be shown. Okay, that requires a lot of effort, but for this moment, just assume it. And the fundamental class is basically generator of this thing that defines a kind of orientation over the manifold. And also, you have to remember that or the orientation of a manifold depends only on the rings. Yeah, of course. And so this, so what this Poincare duality says. So we have a cup product structure, of course, from hk times and h n minus k to r. So how is this defined? So remember that. What should I write? The ring. No, no, no. Not only the ring. I mean, yeah, kind of. It depends on the ring, because if I change the ring, for the case of, for example, if I have Z2, then every manifold is orientable with respect to Z. Okay. So basically, here we have this. Uh, so this is basically defined by take a element alpha here and take a element beta here and define their kind of inner product or any bilinear form like this, which maps to alpha times beta. So you know that this alpha cup beta will land in HN, which is their sum, and you apply it to M. So this will give you a, a element of R. So this is well-defined map. And what Poincare duality is saying, that this pairing is non-degenerate, and this non-degenerate is same as you have seen for the vector spaces. And also this is one of the important corollaries that I will use after this slide only. That if alpha is a element of, so again you have to assume that M is a closed orientable manifold. So if this, in this case, so if alpha is an element of this, so there exists one beta from the co-complement of the, I mean, co-dimension of this K. Okay, so there will exist such beta such that alpha cup beta is a generator of this thing. Okay, so this just follows from uh, the definition of the non-degenerate pairing. And so remember here, this K has to be a field. For any arbitrary thing, we cannot say this. Okay, so yeah, so here I will just give the outline of computation of cohomology ring for RPN with the coefficient in Z2. So as I have already said that the I mean, if we fix the base ring to be Z2, then the every manifold is orientable. So we don't have to bother about orientability of Rn. Like if, if the base ring was R, on that case, like RP2 might wouldn't be a orientable thing. But for if I take the coefficients in Z2, every manifold will be orientable. So yeah, so RPN is orientable, and now it is a very good exercise to prove that it is. I mean, the cohomology groups for k less than equal to n is just Z2. So basically, for this, what you need to use is CW structure of RPN, that at every dimension of RP, yeah, at every dimension there is only one cell, and you have to do some kind of you have to compute the homology first, then you have to use the definition that I have given to compute the cohomology, and also you have might have to use this universal coefficient theorem. So yeah, uh, again, so RPN has a CW structure like this. So at every dimension k, there is so this RPK is the k dimension skeleton. So basically, what it will say is that this inclusion RPK k to RPK plus one. This is isomorphism in cohomology for I less than equal to k. Yeah. So this will help us to say that if alpha is a generator of this H1, so basically, here we will prove this inductively. If alpha is a generator of H1, then we know that there exists some element in this. So yeah, so by the already I have mentioned. So since we know this RP2Z, so basically, uh, so okay, sorry for this. So if alpha is generator of this, so by the thing I have mentioned previously, since this okay, since this Z2 is a field, we can say there exists some element called the K alpha, such that this cup product will be the generator of H2 of RP2. Okay. Now, just it can be just shown by via some computation that this k is basically one. So basically, alpha square generates alpha two, and we will continue doing this induction process until we get to n plus one. And since there is no cohomology of RPN above n, so this alpha to the power n plus one will be zero. So basically, what we have seen that the corresponding cohomology ring is basically given by this polynomial ring. Okay, and there is also a kind of an open-end problem that if we have a kind of polynomial ring, can we construct a space? You have that cohomology ring. So basically, there is some work done. So given any, yeah, I think, yeah. So given any if I remember correctly. Yeah. So given any polynomial ring over Q, I can form a space that comes from, I think that comes from some kind of rational homotopy theory construction, that there exists a space whose homology ring is that. And for in general, even for just ZP kind of thing, it is not known till now. So yeah, that is a open end problem. So and we can just use the similar kind of cellular decomposition of this RPN. So in the case of RPN, what we have seen that each dimension has only one cell, and for the case of CPN, we will see that every dimension has only one cell, and other dimension doesn't have any. So we will just carry out this similar kind of computation on this case to compute the cohomology. So here is the first application, that is Hopf invariant and H spaces. So before going to the Hopf invariant or H spaces, I will address one problem. So this is the problem when Rn is the division algebra. You might have seen during your uh, rings and module course, because it is very interesting thing. So when is Rn is division algebra. So here I will make some remark, like division algebra is a thing which has a product and an identity element, and also like this map x goes to a times x. So if I fix a element a and x goes to x times a, they are linear isomorphism for a division algebra. So I can use this property to get um to get a map, because these are linear, so it will respect all the conditions. So we can take the corresponding quotient, and I will get a map from rpn minus 1 to rpn minus 1, I mean their product to rpn minus 1. And so this will induce a map in cohomology ring. So basically, since cohomology ring is also corresponds to a contravariant function, so everything will be get reversed. And since we have I have already mentioned that if I have where I have mentioned that, yeah, this thing. If I have two space, their product will just be the tensor product. So yeah, so the this corresponding cohomology ring will just be this. And yeah, so for since alpha is the generator here, it will map to somewhere here. So that is something k1 alpha 1 plus k2 alpha 2. Now it can be used that this since these are isomorphism, this will induce some kind of homeomorphism when we restrict this map to like rpn times a point, or a point times rp1. So from there it can be shown that this k1 and k2 are 1. So basically, what we get is that this under this morphism, alpha maps to alpha 1 plus alpha 2. And since we know that alpha times n, I mean alpha to the power n is 0, so we can see alpha 1 plus alpha 2 to the power n is 0, which means every coefficient, every binomial coefficient here are 0 mod 2. Because here alpha 1 and alpha 2 are some generator, so it shouldn't be depend on alpha 1 or alpha 2. So and by some simple number theory thing, you can show that here n has to be a power of 2. So and so there is more we can say about this. So for that, I will introduce the notion of Hopf invariant. So for the case of Hopf invariant, so consider a map f that is from S2n minus 1 to Sn, that is a continuous map. Now we will consider this adjunction space. Okay. So I think everyone is familiar to this adjunction space who are taking a course on topology. So yeah. So now if we compute the cohomology of x, it will be z in the index n and 2n and 0 otherwise. So the easiest way to see is, so just consider the cellular decomposition. So it has only one 0 cell and n cell for this Sn, and only 2n cell for coming from this Tn. So basically, yeah, from there we can just conclude that it has a cohomology n or 2n and 0 otherwise. So if alpha is generator of this cohomology, then alpha square, as we have seen, that it will land in the 2n dimensional 2n dimensional cohomology. Yes. So and if I have something, the beta is the generator of H2n, then we can say that alpha square is equal to k times beta for some k that belongs to the ring Z. And here is the thing: this can be shown that this k only depends on the f, or rather, it depends only on the homotopy class of f. So basically, yeah. So this is what it is, and this k number is what we call Hopf invariant for the map f. Okay, and we denote it as HNF. Now here, this is the thing I want to say. So basically, in the evening talk, Shomo will define what is homotopy generally. I think he will more generally define the homotopy groups for relative pairs. But here, just remember that whenever I am talking about this, this is just the set of all morphisms. Morphisms mean here the continuous function from Sn to not x, yeah, sk to x up to homotopy equivalence. So that this is what I mean when I'm talking about homotopy groups. So yeah, so this gives us a morphism in the case of this. Now, okay, so now some comments on this map. So there is some very interesting thing that shortly I will show some Hopf invariant for the case of n equal to 2. Then you will see there exists a uh, Hopf invariant one thing, and and except for the case n equal to 2, there is no other number for which this h is isomorphism. Only for the case of n equal to 2, this is isomorphism, and for there is some modification that I don't remember actually. So I think for the case of n, when n is odd, it can be shown that this map is a trivial map. Yeah, this also at the end of this talk, you will see by Serre finiteness that this map is trivial when n is odd, and for n equal to even, there is something we can say, but yeah, so here is the example of Hopf invariant. So basically, we can treat S3, which is this sits inside C2 like this, and S3 is basically this thing. And so there is a natural projection from S3 to CP1. What is this? So this is basically S3 quotiented S1. This is isomorphic to, I mean, not isomorphic, homeomorphic to CP1, and CP1 is homeomorphic to S2. So those who have seen quotient spaces might have seen this, but at this moment you can just assume this. Okay, so corresponding to every point here, there is. So if I take any point here, inverse image of this will be a map of I mean, inverse or image of this here will be also a point. So if I take, so here is a quotient map, right? Yeah. So here is a yeah. So here is a quotient map, and so every point here will represent a point here, and this point here will represent a circle. So every point, if I look at its fiber, that has S1. So basically, it can be shown this is a fiber bundle. Don't bother about the fiber bundle thing. Just I have written it. So yeah, and it also can be shown via DRAM cohomology that pi has Hopf invariance one. So and also since I have already said that every ordinary cohomology are same, so for the case of DRAM cohomology also that will be isomorphic to the singular or simplicial cohomology. So yeah, now we will arrive to this question for which n this Hopf invariant is one. So Adams has a very good paper. I forgot the name of the paper. So there he have proved that Hopf invariant one can exist only for the case of n equal to 1, 2, 4, and 8. And here is a definition of H space. And now what I will do, I will relate this H space to the Hopf invariant one problem, and then we will go back to the division algebra problem. So here, if I have a H, so basically I have to define a H space. H space is nothing but a generalization of a topological groups. Basically, so here we have a product that is from x times x to x, of course, and identity E, such that this map x goes to the product of x times E, and x goes to E times x. They are homotopy to the identity. Now remember, for the case of topological group, they are just the identity maps, but in this case we are generalizing the definition to be homotopic to the identity. So this is what we call H space. Now for example, we can see that this space S0 is basically 2 points. So on that case we can define a group structure. And also like S1 and S3, we have seen they have some yeah they have some uh, they have some a group structure that comes from real, complex, and quaternions. And A7 has a H space structure that is not a group structure, because this thing will come from the octanions, and there the product is not associative. So yeah, so this is the thing. And also from here I can uh, give a question like, for which n Sn minus 1 admits H space. And Whitehead has proved this, that this question is equivalent to asking for which n there is a Hopf invariant one. Now one can easily prove that Rn has a division algebra if there is Rn has a division algebra structure if there is this Sn minus 1 has a H space structure. So this doesn't require any algebraic topology or algebraic geometry. This is just some basic computation you can do. So due to the constraint of time, I'm not able to do that. So basically, from here we can conclude that Rn can be division algebra only for n equal to 1, 2, 4, and 8, and we can see all of them are power of 2. So basically, yeah, this is the thing, and this is a very nice diagram that I have taken from the paper of Adam's paper. Yeah, so the name of the paper was on Hopf invariant one problem. So here he have I mean mentioned all the chart that was proved till that date, after he used some kind of theoretic thing to prove that the Hopf invariant only exists for 1, 2, 4, and 8. Okay, so now. Yeah. So basically, what I have said is this thing I have said, and I have said that this can be also proved, and this is via Whitehead. I mean, Whitehead had proved that Sn minus 1 is A space if and only if there is Hopf invariant. No, no, this 1, 2, 3, 4 you are saying these all are proved by Adams. Yeah, all these things you are seeing here labeled, these are proved by Adams, and rest were proved earlier. Hmm. Thanks. So now I will. I was planning to show some construction of, I mean, James construction EHP sequence, but I won't be talking much about EHP sequence. But I will talk about James construction. It is a very important construction, because given a space X, the James contraction Jx give us a monoid structure, or a monoid, and there the product structure helps in many things. Like there is a paper by Adams only on Jx groups. That is a very nice paper one can look up to. So basically, recall that RP infinity over Z2 has ring this thing, because I have already proved that RPN has something Zx quotiented by x to the power something. Since we are taking that n to infinity, it will have the cohomology ring Z to x. And also the cellular structure, I have already said that RP n has one cell in every one dimension less than equal to n. And so yeah, so for the case of RP infinity, in every dimension we will have only one cell. And so basically James tried to construct similar kind of spaces. So when we are given h to n, we want to construct a space out of it such that its cohomology ring is kind of similar to ZX. So basically, why is it? Because there is many things include that cohomology operations like Steenrod and the Steenrod operations. They give many information about the spaces or that algebra. So if the space is some similar to the ZX, that will be very helpful for the yeah, that will be very helpful for some computations. So here for James did, so given a CW complex X, he constructed a space Jx. Now here I have written CW complex for some reason, but it can be done for any topological spaces. So basically here you have to fix a point E, and this JIX, this is the quotient space of x to the power I. And here x to the power I is the I many products of x. And here the quotient is taken under this equivalence relation, that whenever E comes here, we will try to neglect that. So the reason of this equivalence is that you can see that this gives us kind of a product structure. So basically, if we have something like, if I talk about only x2, okay, then what it is saying that x1 times e, and this is identified to e comma x1, right? So basically what we can say that x1 e is something like this. So basically it helps us to give a kind of a product structure. So basically okay, now when we'll see that jx, this product structure will come from here only. That so, and there is a natural inclusion gix included in gi plus 1x, just given by this inclusion. The and here, this, since we are taking the identification, it doesn't matter where we are taking this e. कहाँ? I said in something like steamroad operations or steamroad algebra. If the ring is ZX, then we don't have to bother much about this. Like if I remember correctly, the standard algebra, which is SQ, it gives us, so in the case of, and it somewhat helps in terms of looking at, I mean, so basically what we are doing, we are looking at many more, as much as many invariants possible. So this also gives us some kind of invariant structure that I forgot, that like, there is some relation between this standard operation. I don't remember exactly, but there is something like this. Is standard operator q, this gives us 0. So I don't remember the coefficient. The coefficient are some in terms of binomial coefficient. I don't remember them exactly, but yeah. So this is one of the things. And yeah, so for this case, this so here what we are doing. So whenever we have e at whichever position, it doesn't matter. We will identify them as a point. So basically, what it helps, like it helps us give, I mean, giving a kind of product structure. So and also there is a, sorry. So there is a inclusion like this, that xi to xi minus sorry, x1 to xi goes to x1, and here this e you can put wherever you want. Okay, and so under this inclusion, you can take the co-limit, and you can construct this jx space. And this space is very interesting uh, because here basically, if you have you will identify a point like this. Okay, x1 and x2, this x1 belong to x, and this also belong to x. And x1 x2, this means you have x1 x2 and e in the rest of the places, and you can move this x2 wherever you want because of this identification. So this helps us to give a product structure in this zx. So that's why I've said that this has a monoid structure, because we don't know about the inverses. Hmm. Yeah, they are already in JX, na? Yeah, you can take any arbitrary point in JX. Okay? So by this co-limit thing, that they will land in some of the JIX. So there you can identify them as a product and you can do the thing. Okay. So should I move to JIX? There is no product. I'm saying I can give a product structure like this. So basically, this will induce kind of a product structure. See, you have a point E. You are, I mean, wherever this is position, that doesn't matter. If I have the rest of the components same, then they will give us same kind of thing. So basically, you can treat like this x1 to xk to xi. These are some elements, and here also xi. These are the elements, and you if you take all the products, they are same, right? So this equivalence is saying us that thing only. So yeah, this thing I can think of as a product of like x1 to xi. Yeah, no, jx. See, x is already included in jx, right? See, because here this I. So if you take I to be one, then jx is only x, right? So x is already included in the jx. Exactly. And also it will, I mean, you will see that for the case of sphere, I won't write it here explicitly. For the case of sphere, this GIX exactly gives us the I-dimensional cell structure of the space JS. So, huh? No. Oh, if I, yeah, of course. Yeah, of course. Yes, yes. Hmm. Okay. Thanks. Fauci. Okay. Hmm? No, it is working. What was something was okay. So again, so this is the thing I was talking about that JH2N has one cell in each dimension. So basically, you can just uh, you cannot see even it properly, but what you can see is like so basically this JX space we have some product. So we have this union of xi for I greater than equal to one. So basically, and under some quotient. So basically, you can see that for every such 2nk dimension, there is exactly one set. And so you can compute the cohomology corresponding. So that will be z for the indices. This is the easiest thing. And so yeah. So now if you assume that xk to be the generator of this cohomology group, then of course the cohomology ring will be generated by these modules, because we know that the cohomology ring is nothing but the direct sum of this thing, direct sum of these cohomology groups. So basically, and this relation is very important relation, that xk is equal to x1 to the power k by k factorial. And to prove this, I think you need to do a lot of computation, but that is not very hard thing. So in my notes, I have written this. So if you want to look at that, you can look at the notes. I think it will be uploaded in the Math Club website. So yeah, and so from here, okay, so I have written something mistakenly. So this will be just a star, because this is the cohomology thing. Okay, so this is isomorphic to a z module that is generated by xi to the power I by I factorial. So we call it like gamma zx. Now you can see for the case of zx, what we have? We have the generators that are 1, x squared up to something that is going on. And here the generator is 1, x squared by 2 factorial, it is going on. So, and basically this is not zx. That's what I want to say. But if we take this ring, and here also you have to change this thing to z. And if I take the base ring z to be q, that will be, I mean, that will give us only the qx thing, because there that 1 by I factorial thing can vanish. And not vanish, 1 by I factorial thing belong to that q thing. So even more can be said about this JSM thing. So here is the result. This is proved by James that this cohomology ring for JSN is isomorphic to gamma z x as defined here. So if n is so this is for n equal to n is even, and for n equal to odd, this is isomorphic to this space. Now this construction. So here is something I will just state, I won't prove anything here. Uh, yeah, yeah. So for n even, this is the isomorphic thing that I have said here. And for n equal to odd thing, this is isomorphic to this complicated space. So this HNX is, this is nothing. Basically, this has only one element in nth dimension and other thing is zero. And this is the thing I have said over here. So basically, and also like this ring, it can be written as an exterior algebra thing. Okay, this is equal to, so basically here x, degree of x is a. So here is the thing I want to say, but I won't say much about this. That is, so Whitehead proved that there exists a long exact sequence of homotopy group. In the evening also, you will see many things about the homotopy group of sphere. But yeah, so computing homotopy group of sphere is a very open problem and very difficult problem. And so for n greater than equal to 1, there is a exact sequence that was given by Whitehead, and he has proved. I have looked at his paper. He has proved it using very difficult machineries. But later, actually, James gave a very nice proof of this using the construction I have said earlier. So here, this E this comes from that this comes from suspension only, and so suspension is basically, I think everyone is familiar with suspension. Yeah. So yeah, so here the suspension E comes from the German word of suspension, and H is secretly Hopf invariant. I want to talk about this, what is H, but I won't be able to talk about this. Sorry for that. But I have mentioned this in my note. Once again, you can find it in the web page of MATLAB. So here is okay. So I have talked about this, and this reference I was talking about on the groups of JX. So here, there he have defined one more thing, like the reduced JX group. That is a very interesting thing one can look up. And yeah, so huh? What? P is nothing. P is something that is joining this. I mean, once we have some kind of a fiber sequence from there, if we take the long exact sequence, so that long exact sequence, this P comes from that joining thing, nothing else. Here E is, I mean, kind of suspension. This is not exactly suspension, but this you can visualize it like a suspension, because suspension, what it does, I mean, it induces in higher dimension, right? See, that's what I want to say. That Whitehead did it in a very peculiar way. But if you follow the path of James Watt, so he have proved like this comes from a fiber sequence. So that's what I wanted to say. But I won't be say much about this. So let's see. So if we have a fiber sequence like this, so then we because see, whenever we have a fiber sequence like this, we will get a corresponding long exact sequence in homotopy groups. I think Somo will talk about this in afternoon. Yeah, so our first case should be that long exact sequence comes from some kind of fiber sequence. So and we will try to guess what is the fiber sequence. So for that, just note that this homotopy group, this is Z. Okay, and here I have used suspension loop adjunction. So we will again talk about it. And so here we have a, so since this is non-trivial, so we can get a map which is not homotopic to identity. So that will be just assigned to this loop space. And this is for sphere. Oh, brackets is this thing where I have defined homotopy class of group. I think I have erased that. So basically, this is just formed from what. So if I take it like this, so this is basically is into X, all the continuous maps under the relation that under the quotienting that they are, whenever they are homotopy, they will be in the same class. Omega means the loop space. So whenever you have a space, omega x is the set of all the space. Sorry, all the loop. You when you have fixed a base point. Yeah. So yeah. So yeah, so from here, what should be our guess that this is a continuous map. So whenever we are given a continuous map, you can construct a homotopy fiber to it. So if is the corresponding homotopy fiber, so this will be the our fiber sequence. And if we look at the corresponding long exact sequence in homotopy group, what we can guess from here, this F. So this F has to have. I mean, we expect this to be this. So because let me get back to that thing. So here, okay, I should have write it here. Okay, just let me mention. Okay, here this since we are applying loop, so what does it do? Is like k minus one loop of x. Is this right? Hmm. So, hmm? Yeah. So we will just use this. Like here, you can use that to get here. You will get what? You will get it as pi k plus two of s n plus one. Yeah, pi k plus two of s n plus one. So basically, this is where you are the at the end. So basically, if you compare it, eh, so basically, you will compare it to the compare it to that long exact sequence, and you expect this fiber to be this. Basically, what you expect that you will have a fiber sequence like this. Okay. Now, for any fibration, exists a fiber sequence like this. Apply loop stream. So from the James construction actually helps us to give us a map that is from this loop space of Sn plus 1 to the loop space of S2n plus 1, and its fiber that should be computed to be Sn. So if I take corresponding one shift of it, what will be there? So there will be sigma square is 2n plus 1. So this is what we are expecting. So this is how we get that fiber sequence. And if we apply the, so basically this comes from the James. Okay, so this is what I wanted to say, but I won't be able to talk about it much now. So yeah, so for details you can see at the notes. Now I will talk about this self-finiteness condition, and uh, here also one more thing that won't be clear within few minutes, that whenever we are given some kind of homology, we have the multiplication structure that will help us to give us something called spectral sequences. And for the case of homology, for the case of homology, we don't have this kind of product structure, but we have something called co-algebra structure that will also help us to give a product structure in spectral sequences. So just for now, take this as a definition, but this is not a proper way to motivate for spectral sequences. So spectral sequence is something like this. Here also I have to write it. Okay, so you can look at this definition, but this definition is very abstract to understand. So basically, you just consider a double complex. Okay, so basically at the beginning, you have some complex like this. K01 to K02 to, sorry, K11, and here will be K21. Yes. So basically, so you have kind of infinite grid here, and here what you will do, you will take cohomology of these arrows to get a new kind of graded thing that will give us. So I'm writing it like K of 00 hat, and here you have this map. So here K01, here this, and in this case your maps will be like this if I'm writing it properly. So basically, you can see that this is a sequence of quotient complex at every and every when you are increasing the dimension, you are getting it by taking the corresponding cohomology. And this dr, that is the differential operator. In this case, here this was the differential operator, and in this case, this is the new differential operator. This so, and also in terms of Hatcher, we call it U0 page. This is we call E1 page, because I mean, you can look at like a book where you have the first page started with the with this double graded sequence, and then you move to this, and you continue doing this. So yeah, so this is what a spectral sequence is, and here is the theorem by Serre and Lave. So there is a very good story about Lave, that when he was in jail, he proved this thing. So that is a good way to do math. Okay, so so whatever it is, so whenever we are given a vibration or fiber space, whatever we want to say, if included in E to B with F being simply connected, then there is a spectral sequence whose E2 page look like this. That is basically, so this is basically cohomology, but the coefficients are coming from the cohomology of F. Okay, so and if so, basically, what is it? If I take a field, this will be very nice to understand that this HQ of B coming from this F, and the coefficient are from, let's say, Q. Okay, then we can say it, this is isomorphic to, and again here I am using universal coefficient theorem. For those who don't know, don't worry, just take it as for this moment. So for the case of field, it will split like this, and that will be a very interesting thing. Okay, so hmm, yeah, yeah, HQ. So basically HQF. So F has a cohomology, right? Q dimensional cohomology. So you were measuring the cohomology of B with respect to that being in the coefficient. Huh? No, no, HQ. No, there is no cup product. So this is the coefficient, right? So this is the coefficient. So if I fix a field, not field, called, if I fix the base ring to be Z, okay, then this is some kind of a Z module, right? This is also a Z module. So basically, whenever I have a Z module, I can define cohomology with respect to that. So basically, what should I do? Okay, just I will take few minutes. So suppose we have this. Let's get back to the quotient complex. Okay. This. Okay. Now what we'll do, we will apply this function, and here, yeah. Okay. So again, we will get a quotient complex and take the corresponding cohomology. That will give us a cohomology with coefficients in M. Okay. And here this M is basically this HQ. Okay, now recall this KZ in this denotes Eilenberg-steenrod space, whose nth homotopy group is Z and rest are the trivial groups. So basically, it also can be shown. It is a very good exercise actually to show this. Actually, this is not very hard to prove that this is isomorphic to QX for n even. The harder case is to prove I mean, the harder case is to find the cohomology ring when n is odd. But for this moment, I will just take the result for n. And so again, from the description of the Eilenberg-Maclaurin space, we can say that this is Z. So there must exist a map which is not null homotopic. So take this map F, and we know that any vibration, yeah, sorry, or any continuous map can be decomposed as a homotopy equivalence and a vibration. So basically, we have this continuous map F assigned to this Eilenberg-Maclaurin space. So here we will decompose it like this. This is homotopy equivalent, and this is the vibration. And corresponding to this vibration, F is the fiber. Okay. Now, for this case, if you take the corresponding log exact sequence that I have mentioned earlier, you will see that the homotopy group of this fiber is 0 for I less than equal to n, and this is the homotopy group of sphere for I strictly greater than equal to a. So Serre finiteness condition says us something about the higher homotopy groups of sphere, that except for some cases they are finite. So basically we are heading towards that one. So yeah, so basically we have this. Okay, let me get back to that. So here we have this inclusion. Again, we can split it like this. This thing, that this is homotopy equivalent to F, and this is the vibration, and F had be the corresponding. F had be the corresponding uh, fiber. And again, if you take the corresponding long exact sequence in homotopy group, you will find that this is basically a Eilenberg-steenrod spaces, because the except for dimension n minus 1, everything else is 0. So up to homotopy equivalence, we have this fiber sequence. Now what we will do with this fiber sequence, we will apply the Serre's theorem that I have mentioned previously. So yeah. Now here we will use that search theorem with coefficients in Q, and the reason of taking coefficient Q is that I have already showed that this actually splits in a factor, so that will be easy to compute. So basically, the spectral sequence, what will it say? So let me write it here again. So if you so corresponding to this, we will have a spectral sequence whose E2 page is uh, E2 page is look like HP of this is a coming from the fiber. Now, for the case when n is odd, I have already I mentioned that for the case when n is odd, this n minus 1 is even. So, for the case of even, the corresponding cohomology ring looks like Qx. So, basically, at each dimension, there will be n. So, basically, if I write the spectral sequence, it will look like this. At the 0th level, it will all be Q, and above here also Q, 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 and the corresponding thing here will come from the tensor product that I have mentioned earlier. Okay, I yeah. So this will be something like that. So this spectral sequence will help us to say that there is a map here, right? I have to. So these maps will be isomorphism. So when we'll take the next, we'll go to the next page called E3. Then all the corresponding cohomology group will be zero. So if the all the corresponding cohomology groups are zero, then let's get back to the Serre's theorem. What is it say? That E infinity. I mean, we are taking this cohomology again and again until we get E infinity. This will converge to the cohomology of E. So basically, what we are getting, that we are getting the cohomology of E is basically zero. So here, what we are getting that cohomology of scripted A, or cohomology of this A, because they are homotopy equivalent. Their cohomology are basically zero in with the coefficients in Q. So, and since these are the coefficient in Q, and we know they are dual, so we can say that these homologies are also trivial. Now there is a very nice theorem that this is basically a rational homotopy theoric version of Hurwig's theorem, that whenever I is less than equal to R, this is isomorphism for these indices basically. So uh, smaller, see here, that's what I have mentioned. If this is trivial for I less than equal to R, then this is isomorphism for these indices. So this is not the same R here. Here these are I mean, that is the use of the rational homotopy theory. So here if you apply where is the space? Yeah. So in this case, so this is basically n minus 1 connected. So you will apply this thing, that this homology group is trivial. So you will, what you will get? Like you will get for up to these indices, the corresponding homotopy groups are also trivial. Now you keep on doing this. So what we will get? We will get the corresponding cohomology, sorry, corresponding homotopy groups with the quotient. They are also trivial. So this says, and also there is a theorem that if X is a finitely generated CW complexes, then the homotopy groups are also finitely generated. So here, after taking the what is it, tensor product with Q, we are seeing that it's trivial. So it means uh, there is only yeah, there is only the finite parts, or there is only the torsion parts, because if there was free part, it shouldn't have been zero. So that is the reason we can conclude that we can conclude that this pi I x has only the torsion parts, and for and since x here is basically what we have shown, that for higher dimension this this f is homotopy to this f homotopy group of f is isomorphic to homotopy group of this one. So there we can uh, there we can conclude that the corresponding homotopy groups are just finite. So this is one of the important results, that for whenever n is odd, so this is finite for I less than I strictly greater than n. Now use the EHP sequence that I have mentioned earlier. So you will get that pi 1 of Sn is finite except for this case. So this is the theorem I want to conclude with. Yeah. So this is the theorem. So done. Fine. Any question? Any question is allowed. Whatever you can ask. Okay. Mhm. No, no, we guessed it. Okay. We guessed it just from this. So this is the long exact sequence, right? We are getting from this fiber sequence. So we just guessed it with the EHP sequence. We just compared it with the EHP sequence to guess that this F can be the omega 2 of S2n plus 1. Yeah, James construction has a very important use. So I say that this map doesn't come naturally. This comes from the James construction. So there is one thing that it can be shown that Jx is homotopy equivalent to this space. So this is one of the important result that I want to use, but due to time constraint, I have to remove this. So this we will use to prove that there exists a map like this, and again we will use that any map can be factored to the some kind of homotopy equivalence and fibration and take the corresponding log existence. So this is what the idea. Hmm? If not, we thank the speaker. Thank you so much.